All right, so what I wanted to talk about today is an overview of the Cray performance tools. I wanted to go into how we use the Cray performance tools to identify the slowest areas of a program, and then talk a little bit about some tips for analyzing program performance. So the first thing to note is that one of the main goals for our development of the performance tool software at Cray is that we want to reduce the time investment associated with porting and tuning applications on Cray systems. We want to give the user the ability to analyze the, touched the wrong thing here, to analyze the whole program behavior across many nodes. So not just focusing on a single node, but identifying critical performance bottlenecks within a program. Also, another goal is to improve the user's profiling experience by having a simple interface and an advanced interface. So a lot of times users don't tend to tune or profile their applications as regularly as, for example, compiling codes. And so you may not remember how to use a performance tool. And so we offer a very simple solution to be able to get your top time consumers. And then because some people do need to dig into the depth of tuning, and because applications, especially in HPC, are very unique, we have a lot of capability to handle things like controlling the amount of data that's produced or focusing in on certain areas. So basically our goal here again is to make it less painful to analyze the performance of an application and to be able to analyze applications at scale. So from a quick view of what we offer as far as functionality, we support all the programming models that are supported on Cray systems. So we support MPI, SHMEM, OpenMP, PGAS, OpenACC, and CUDA for those systems that have GPUs. We have with the tools a sampling and tracing capability. The light mode that we're going to talk about today really uses sampling, and I want to show you how much information that you can get with something that simple, especially because it can really it has the least amount of overhead, it creates the least amount of data, and that's the mode that is most likely to be used with applications that are running at large scale in production. We also have, with tracing, we have two different modes. We have a summarized mode where you get a profile of your application based on tracing, but it's a summarized version. It's not a timeline view, it's not a sequence of events. We also offer that, but that again is something that users need to be a little bit more careful with because that can produce an awfully large amount of data. The performance tools, just to remind everyone, I don't know how many of you are familiar with them, but they support the Cray programming environment, so the Cray compiler and libraries. We also support the Intel compiler and the GCC compiler. So you can profile your code with the Cray tools with any compiler that you're building with on the system, or at least those three compilers. We do have more capability with the Cray compiler than we do with the Intel and GCC, and we'll talk a little bit as I go over, there's certain features and functionality that's available with the Cray compiler that's not with Intel and GCC. So it depends on what you're doing with your application and what kind of information you get. So the components of the tools, we have CrayPat and CrayPert-lite. I'll show you how we're going to focus on the light mode here. We also have PAPI. We offer PAPI, which is, it gives you the performance counter information. We use it actually internally by the CrayPat software as well. So the user can use PAPI themselves, or CrayPat will use it when it's collecting performance counters. We have a visualization tool called Apprentice 2. So sometimes it's nice to be able to visualize instead of looking at text reports. It's easier maybe to see excessive communication or some load imbalance. And so sometimes that's a very nice alternative to the text reports. The text reports, which we generate by default, are very useful when you're on a Cray system and you want some quick information about where you're spending your top time consuming routines. And so most of the information I'm showing here is going to be just the simple text tables. The final component is Reveal, and this is a tool that allows you to view the Cray compiler optimization messages. It also allows us to show you key loops in a program that would be most important to try and parallelize. We can give you high bandwidth memory traffic, and also the tool will assist with adding OpenMP to a program. So just a little bit of information on where we're at with our releases. The current release was released in December of 2017. It's our 7.0.0 release. So I'm not sure what you're running on Theta, which version, but that is the most current version of the tool. We do plan to release again in the spring with an update with some additional functionality, but the 7.0.0 release added some significant performance improvements for execution of our Perftools-lite mode so that you can run applications at much larger scale. The performance data experiment directory is also new. So one of the things that we did is we took all the data that the performance tools generate as part of analyzing and collecting data for your application and put it in a directory. So it's not, there aren't files spewed all over your directory. And this single directory has a unique name and everything is included in that directory. The nice thing about it is the tools know how to understand the hierarchy of the directory so that you can still use the different utilities on the directory itself. And we can talk about that a little bit more going on. We also added some memory and vector sensitivity metrics. It depends on the processor that you're analyzing. And really it depends on the performance counters available because we do rely on performance counters. And so the more capability there is for the processor to analyze, the more metrics we can provide. So those are some things to take a look at if you've not tried the 7.0 version yet. So quickly, how to access the performance tools for those of you who are not familiar with it. We use the module system at Cray. We have the GNU software modules, and the Perftools base module is a module that gives you access to the software stack. It doesn't do anything to your application at that point when you load it, but it puts the documentation and our binaries in your path. So let's say you did some data collection the day before and now you want to run Apprentice 2 to visualize your data. You can do so by just having the Perftools base module loaded because you can access the Apprentice 2 utility. So as I mentioned, it doesn't impact any of your application builds. You really need to load a second module once you choose your instrumentation that you want or the experiments that you want. I think we did set it up so that the Perftools base module is loaded by default. Sites can turn that off if they want to. If it's not loaded by default, you can certainly do so yourself. But that turned out to be just easier so that users didn't have to load multiple modules. And because we don't affect the applications when this module is loaded, it should be safe to do so. So once Perftools base is loaded, then you could do a module avail of Perftools and see what sort of experiments are available. We basically created a group of instrumentation modules. So here in this example, I did a module avail Perftools, and this is a set of the modules that are available in the 7.0.0 release. So we have Perftools, which is our full advanced capability, Perftools-lite, which we're going to talk about here. We also have a couple of other lite modes. Two of the other ones that you may be interested in are the lite loops and the lite HBM. The lite loops we'll talk about later. I think we can talk about both of those when we talk about some specific experiments to perform. So basically, Perftools base, if it's loaded by default on Theta, the next thing you have to do to collect any sort of performance metrics for your application is to choose one of these instrumentation modules. So we do offer two modes. We offer the lite mode and an advanced interface. These are designed to be able to work with each other. The lite mode is the easiest to use, simple interface. You don't have to really remember how to use a profiling tool. And then the advanced mode has more capability. Both of them give you whole program analysis across many nodes, and they help you identify the areas where your performance is not as optimal. And we did try to make it easy to switch between. So I'll show you some lite mode examples where we actually switched to using some of the more advanced interface. So the simple mode has fewer steps, it's easier to use, and it provides a condensed text report. It performs data, the big key here to remember is it performs data processing and report generation at the end of the job automatically for you on the compute nodes. That was one of the things that we did in our 7.0.0 release is to enhance that so that it can work in parallel on the multiple nodes of your system that you have associated with your job as opposed to a serial. So if you used it in the past, it performed quite slowly if you had a large job because all the work was only done on one node, and now we can actually work on multiple nodes. And as I mentioned earlier, you can mix the simple and the advanced interfaces, and I'll show you how. Okay, so that's an overview of the performance tools, basically the set of utilities or products that we have in our suite and the type of capability that we have and how to access them. So now let's talk about light mode and how you identify the slowest parts of your program using the light mode. So this is an example. I assume that I have the Perftools base module loaded. This is an example of how I would go about collecting performance data using the simple interface. So I load the Perftools-lite module. I build my program the way I normally built it before. And at the end of the build, you should see, or during the build, you should see a message coming from Cray saying that it created an instrumented executable. So that's a good check to find out if you really did do what you thought you did. Look for that message. Another thing we suggest is if you're building with the Cray compiler, it's very helpful to build with the listing or to generate a listing. So we suggest you add -h list equals A to your build. That is optional, it's not needed, but it can be used with the Cray performance tools when you're doing loop analysis to really work on tuning loops. And we'll look at some examples or talk about that in a little bit. So you build your program. Technically, you don't have to add the -h list A if you're using the Intel compiler. You don't have to change anything. After you build your binary, then you run your program the way you normally do on your system, so either an app run or srun, depending on your workload manager. Your program name is the same as it was before, but it is instrumented to collect performance data. The performance data will be sent to standard out in text report along with your application output. It does also get sent to the directory with the unique name that I talked about. And one of the things that you can do is you can use a listing, a compiler listing that has line number information to help correlate with things. We do correlate to line number, and I'll show you an example of that, but you can get more information if you happen to have that listing as well. Okay, so really quick, the compiler listing, just to show you, we do offer with, when you build with -h list equals A, we tell you what the compiler did to the code. So in this example, the outer loops were blocked and the inner loops were vectorized and unrolled. So you do actually get some feedback on what happened within your loops if that's what you're going after as far as tuning. We also tell you why optimizations were performed. So for each line number of each loop, we tell you if it was vectorized or blocked, or why it wasn't vectorized, or why something didn't happen. So we have the concept of positive and negative messages. So this can be useful.
Hey, Heidi, there was a question about if there were any particular build options that will make Perftools-lite work better or worse. In particular, it's helpful to enable debugging symbols or use dynamic versus static linking.
So we support, so actually what happens when you load the instrumentation modules, so Perftools-lite, for example, what we do is we send some flags to the compiler automatically for you to collect symbol table information. And so you, the user, don't have to add -g, for example, to your makefile. You shouldn't have to change anything in your makefile. We do honor the optimization messages. We do actually collect as much information as we can given the state of your application. We'd like to analyze the performance of your optimized application because that gives us the most, it perturbs the behavior the least amount. So it gives you the most realistic view of what's going on with your application. So no, you shouldn't have to add anything specifically with the compiler with any flags to make it work better or worse. That's a good question. So some applications may be tricky. The more obscure they are, the more, if it's a C++ application and there's a lot of inlining that goes on, for example, we see the code after the inlining. So we see the post-optimized code. So one of the things that I was going to mention was the loopmark messages and with the listing from the Cray compiler, and you can look at this with GCC or Intel compiler information as well, is if you're not seeing a particular function and you think you should be, one of the things is it might have been inlined. And so in that case, if you're playing around with your application and you're not seeing what you expect to see, you may want to disable inlining. I don't recommend that to start. but it's something to look at if you're confused about something not showing up when you think it should. So if that didn't answer the question, let me know. Otherwise, I'll keep going, and you can ask again if you have further questions. So the next thing is, I gave you the instructions. You basically load a module, you build your application, and you run. And this is the type of output that comes out at the end of the job to standard out. So there's a banner at the beginning that announces the Cray Perftools-lite statistics, and so you can distinguish between your application output and the performance statistics. We give you information about the version of Cray Pert that was used. And then at the very top is job summary information. So we review what kind of experiment you performed. So in this case, I was doing a light mode, which is the Perftools-lite sampling. I ran on 96 MPI ranks, and it tells you how many ranks were on each node. It tells you if you ran with threads or not, so if you had OpenMP threads or not. It tells you how many cores were available per socket, and it gives you a little bit of information about the processor you ran on, which is very good to check if you are accidentally running, especially on our systems in-house, we have multiple CPUs, and if we accidentally run on the wrong processor type, it's good to kind of check that in the job summary. We also, you can see here that I've highlighted this is the KNL output for this particular example. One of the things that we add here is MCD RAM information. We tell you what mode you are running in, if you were running in cache mode or flat mode, for example. We give you your average process time, so how long did the job take to execute, your memory high watermark for the application, and some I/O read and write rates. This is some just high-level, high overview statistics about the application. And then we also give you some drill down information. So the next thing is, where did I spend my time? So here you can see this is a simple text table. It's broken into user, etc., and MPI categories. We try and break the functions as we see them into certain categories. The user functions are basically your application routine, and you can quickly see where you spent most of your time. They're sorted by top time consumers. We also have some imbalance columns. You'll see in column 3 and 4 some imbalance information. Basically there, if you look at the percent of imbalance, the higher the percentage, the more imbalance there is, which means that some of the MPI ranks are not performing they're not executing that particular function as quickly, or they're not getting through as quickly as some other functions. Usually the cause is somewhere upstream. And so it's a very good indicator to try and figure out where you may need to correct an imbalance. The imbalance sampling, the other number to the left of the percentage, gives you an indication about if you remove that imbalance, how much time could you save? And so in this case, if you look up at the top for where it says 100% samples, you can see that I have 55,000 samples for this application execution. You typically want to see 10,000 or more samples to get a realistic view of the application. We've found just from experience that 10,000 samples gives you enough of a good feel of what was going on in the application. So I have 55,000 samples, and out of those 55,000 samples, you can see there's not a significant imbalance here. I would really be just removing a small number of samples in this case. So for sampling, for people who maybe don't know, what happens here is when you're sampling an application, we're periodically checking, as the application executes at a fixed set interval, we go in and we check to see where we are in the application. And so if you're in program, if you're running in your program and you're in function A, most of the time, because it's executing, it has a lot of work to do and it takes a long time to execute, you're going to get more samples in that function. Or if it's called a million times, throughout the life of the function or the life of the program, you're going to see a lot of samples there. So that gives you a feel for how many times you're visiting a part of your program. The etc. column, we'll talk about that a little bit. Basically, that just means that we weren't able to associate those functions with a user function that called them. And in this case, you see there's a memcopy routine that we have, and we don't know which particular user function called that memcopy. A lot of times what happens with that is the Cray compiler, if we built with the Cray compiler, it will do some pattern matching and use the memcopy, or our MPI library will use the memcopy, and so it may be coming from those areas. Then we also have an MPI category. So you can see that in this particular run, out of the total run, I spent 56.5% of my time in user functions, and I spent almost 21% of my time in MPI. So it wasn't significant, but it wasn't tiny. The other thing that we can show with the light mode is observations, and this is an example of one of them. So this is grid detection. In this particular case, we were able to detect a grid, a communication grid. We also tell you if there's a significant amount of time that was spent executing in MPI routines, doing communication, and whether or not it may be helpful to reduce that overall communication by reordering your MPI ranks. The grid detection really is there to help you maximize on-node communication. So it's better in many cases to communicate between two MPI ranks if they're within the same node than if they go across nodes, just because going across the network is always more expensive. We also, in addition to looking for that, we also look to see if your resources on a particular node are being overconsumed, and it may be better to pair an MPI rank that's going off node with some of the ranks that are using resources on the node to help alleviate some of those shared resources. And so we look for different angles to be able to try and help you with your communication. Again, this comes out for free to standard out with the simple light mode. Another thing is this is by line. I told you that if you get a listing, you can get line number information, but you can also get that just to identify your hotspots by line number. And so one of the tables that's included in the light mode is, okay, within this particular user routine, where were my hotspots by line? And so that's very useful. It's a good place to dive to right away. You can find out where your top routines are with the light mode, and you can find out which lines typically have hotspots. And those usually turn out to be some sort of loop. And so we'll talk in a little bit here about what sort of things you can do about that to learn more anyway. So I did a Perftools-lite experiment. I built my program, I ran it, I got a bunch of information, but I want a little bit more. And I don't necessarily want to have to run the program again. So there is more information actually that was collected. By default, we try and give you a condensed report, which shows you what we think is the most interesting information about the data that we collected. We don't try to show you everything right away because we do things like filtering out the routines that didn't take very long to execute. We're really focused on trying to show you where your bottlenecks are. If your program, if you were to see all the data, then it would be up to you, the user, to have to sift through trying to find where those bottlenecks are. And so we try to sort things and filter things to help hone in on the meaningful information. But a couple of things that you can do. So Pat Report, the Pat Report utility is available. It's in your path because we've loaded the Perftools base module. And so if you're doing a light experiment and you want to see a little bit more information, you can generate a full report. The full report has things like notes in front of every table that explains how the data was aggregated. It has all kinds of information. In this example, you can see here, I'm running Pat Report on a directory. This is that unique name directory that I talked about. So you can just run the utility on the directory. It knows where to find all the files, and then you can redirect the output to, which is just text, to a file. Another thing that you can do is that's popular, that's used a lot, is to look at callers or the call tree. So you can run a Pat Report -o callers or -o callers plus source. And this gives you both a top-down and a bottom-up view of your program with a call, the call stack. So if you want to see where all your MPI sends were called from, for example, this is the way to do it. Or if you wanted to see what routines your user function, let's say a particular function in your program, called, then you can see that information. There's also a load balance table. I'll show you an example of that. So it's very useful for additional information about load balance for your program. So this is an example of the load balance table. And basically, we call it a load balance, but what it is, Table 1 in the light report and in our full report gives you average information averaged across the MPI ranks for your application. So when you're looking at load and balance, sometimes an application that didn't take very long to execute could still have a high imbalance. And so it may be interesting to go and see what that imbalance, to dive a little bit deeper into the information about the imbalance. So instead of looking at the average time or the average number of samples that were collected for a function will give you the maximum function time. And what this does is you can look at the imbalance and your max. Now what you can see is you can see your min and max MPI rank and how they compared with each other for a particular function. So in this case, down at the bottom is the most interesting. It's just a few excerpts from this table. I have an MPI send call here. One of them has the max is 8.6 sample percent and the other is 0.9. You can see here that my imbalance is 54.6%. It's pretty heavily imbalanced, and you can kind of get a feel for that between the two ranks and how long they took to execute MPI send routines. So now I'd like to just talk about a few things in the report, how you find things you maybe don't see by default. So again, this is really just the light mode, whether you're looking at a full report because you ran pat report, or if you're just looking at the condensed report by default. So the first thing is CRAPAC can collect most detail about OpenMP. If you happen to have OpenMP in your program, we can get most of the information with the Cray compiler. We have hooks into trace points with the Cray compiler that we don't have with the Intel and GCC. In the future, with the OpenMP 5.0 specification, they'll have a tracepoint API included, and then we'll, as soon as the other compilers implement that part of the specification, we'll be able to have the same level or very similar level of detail that we have with the Cray compiler. So hopefully that's coming soon. The way to identify OpenMP regions in the code, we typically name them by function name and whether it's a region or a loop, and then you'll see an at line with the line number. So for example, if I have a function called A in my program, it would be a.loop at line 53 if I had an OpenMP loop before that,
11.
or an OpenMP directive before that loop. Okay. If you have OpenMP in your program, you do not need to turn it on. You do not need to turn anything on in the performance tools. We collect it by default. You do have to obviously enable OpenMP depending on the compiler you're using. The Cray compiler, it's on by default. Intel, you need to enable it as well as with GCC. But there's nothing special you need to do with the performance tool to obtain information about OpenMP. Let's say one of the things that we do is we show you min, max, and median MPI ranks, or we show you an average information about some performance metric with the output. If you want to see the information by MPI rank, so for all your MPI ranks in your program, or by thread, you can do so. Again, what you're going to do, just like when I talked about using the pat report utility to get a full report, you can also say, oh, okay, I want to see all the MPI ranks because I want to get the lowdown on how all the ranks are doing. Hopefully you're not running with 100,000 MPI ranks because you're going to get a lot of data, but that is useful to do. You can also say I want to see rank 0 and rank 50. So you can specify which MPI ranks you want to hone in on if you'd like. So this pat report minus S stands for show, saying I want to see all PEs or I want to see all threats. As I mentioned earlier, sometimes you may not see a particular function. You think that there's something going on with a particular function. You believe that's where all your performance is, but it's not showing up. There's a couple of things. First of all, it could really not be taking that much time to execute. The other thing is, one thing that we try to do is we try to associate the samples collected with a user routine or function, or a known library function that's called directly by a user routine. So if I have an MPI send call, I'm going to call out that MPI send call, not the low-level Eugenie functions for areas instead, because you're not going to know which Eugenie, where in your program that Eugenie call came from, but you should be able to find out where the MPI send is, especially if you look at the call tree information. And so we really try to say, where in my program am I spending my time? To disable this, however,
Heidi,
you can run pat. Yeah.
There's a question on the chat from Ray, I guess. And it
Okay.
said, speaking about it being a lot of data, do you have any recommendations on the practical limits? I assume this is about the
So
amount
for
of
how
data.
much data that you would produce. Okay, so by default with Perftools-lite, we produce not very much data. We produce the same amount of data depending on it doesn't matter how big the job is. It's very similar, the amount of data. This is because we do sampling and it is aggregated data. So you should, with Perftools-lite mode, be able to run an application at full scale on the system and collect performance data that's not daunting to deal with. As soon as you start tracing, even with the summarized trace, that can produce more data. That depends on how many functions there are, because we trace each function. It depends on how big the functions are. We have controls to say ignore the really tiny functions like sine and cosine if they're, for example, less than 800 bytes in size or something like that. So we can control the size, the amount of data collected there. We can also say only collect data for a certain rank. I know rank 0 is going to do all the I/O, and I really want to see what's going on, so I'm only going to collect data for that. As soon as you're tracing, you're going to produce more data, and so you may need to tweak how much data you're collecting, especially if you're going to run a very large job. The other thing that matters is how much time, how long is the job running. If it's running for 15 minutes or 30 minutes or a couple of hours, it's going to produce a lot of data. We have run with Perftools-lite on, I think this was at LANL. We ran on over 256,000 MPI ranks, and the job ran for a very long time. I forget how many hours this job ran, and we were able to process the data just fine. It did take a long time to process the data, but we were able to do so. So really, we do, with the Perftools mode, we do have ways to control it. By default, you should be okay just doing Perftools-lite. Okay. So again, getting back to not seeing a function, you can run pat report minus capital P, and that will disable this pruning to a user routine. So if, a lot of times with C++ codes, this comes in handy. So if you want a different view because you're not recognizing something, try pat report minus capital P. Okay. You can also get the relationship with the callers and minus P. That might help you a little bit too. So these are tips that you can keep with you, especially since this is being recorded, kind of a cheat sheet for when you're using the tools. Another reason if you don't see a particular code is because maybe that particular routine is because it's filtered out and maybe didn't take very long to execute. You can turn off our thresholding. So you can say pat report minus capital T, and then you'll see all functions, and it should show up unless it was inlined. So if your function is not there and you really want to know where it fits in the grand scheme of how much time all the different routines took to execute, go ahead and run pat report minus capital T. You're going to get more information because you're going to get a line item for every particular or every function in your application, but that's fine. It's something that you can manage depending on how you want to see things. So that sort of talks about, I've got my text report and I'm not seeing what I'm expecting to see. Another thing is if the functions are in etc., like you saw the KNL mem copy, sometimes running pat report minus capital P helps with that as well, because then you get a little better feel for where a particular function might fit within your application. A lot of associating where a sample came from to the application, to the user functions, and to the library routines depends on the dwarf issued by the compiler. So we enable dwarf generation for you when you load an instrumentation module, but it really depends. So depending on the compiler you're using, everybody does dwarf a little bit differently. They hopefully code to a particular dwarf version, but things can always be a little bit different. So if you're using Intel versus Cray compiler, you may see some differences there, just associating with functions with other routines or with parents because of the dwarf that's generated. So it's just something to be aware of. So far what I've given you is when you're looking at report generation, you can generate a full report. You can also use minus capital T and minus capital P to get some more information if you're not seeing what you expect. So as far as documentation goes, one of the things that we do is we supply release notes. If you do a module help Perftools base with the version number of your choice, you don't have to actually have it loaded because it's associated with modules. We'll dump the release notes. This goes for all our products in the programming environment group. So we sort of overloaded the help capability in module because a lot of our end users weren't seeing the bugs, the list of bugs that were fixed or the list of enhancements. We do supply release notes and a release announcement for every release, but it doesn't always get into the hands of the end user. And so it's always on the system. You can do this for the compiler. In fact, with the Cray compiler, we list all the releases from a major release and all its updates. So it's a cumulative set. The other products just do the current version that you request. The other place to go for documentation. Yeah.
I'm not seeing your slides anymore. You may have to reshare your screen. Something.
Okay. I'll try again. And I even did the entire desktop too. I thought that would.
Okay, it looks like it's back. Yeah, I think it just somehow there was a glitch and it dropped them. Okay, I can see them now.
Okay. And in conclusion, no, just kidding. All right, so documentation. If you go to pubs.cray.com, that's the place where all of our documentation is available. So if you want to look at the user guide that's available for the performance tools, it should be there. Also online on the systems, in addition to the release notes, you should have man pages available. The most common ones I would look at are, if you type man CrayPat, that'll be an intro man page. It's the intro CrayPat, but I usually just type man CrayPat. That's a helpful one. Also, the Pat Help utility is an interactive, sort of lengthy man page style. So you can type Pat Help and it's got a bunch of topics and you can kind of dive through that. Just a text-based little utility that gives you information about the tools. So again, available on the system when you're running, it's on the login notes. Okay, so the last thing I wanted to talk about is just a few tips for analyzing your application. So what do you do when you have an application and you want to understand the performance of that application? You want to know if there's room for tuning. You want to know where your biggest time consumers are. So where do you start? So the first thing that we recommend is to determine the problem size or the job size that you ultimately are going to run this application. So if you plan to run this on the full size of the system, you're going to actually want to profile that application on the full size of the system. If you plan to run at most on a few nodes, like tens of nodes, you should profile that application on tens of nodes. The reason that we really encourage this is because a lot of times people will profile on a small node size, or small number of MPI ranks, and they tune and they find all the performance problems, spend a bunch of time optimizing, and then they go and they run on a very large, like tens of thousands or hundreds of thousands of MPI ranks. And what happens with that is a lot of times your performance is your bottlenecks will drastically change as you scale. And so you may have been better off just going for the big hammer, the big bottlenecks at scale first. It may be that if you're running on tens of thousands or hundreds of thousands of cores, you don't need to do those low-level vectorization optimizations within a loop. It depends. If your MPI turns out to be dominant, that's going to be where you're going to start. Then as you knock off the higher bottlenecks, the more dominant bottlenecks, then you start focusing on the smaller. So as I mentioned, the high-level program profile at scale is very key for finding the biggest bottlenecks, okay? And this, again, is really just our suggestion for honing in on giving you the biggest bang for the buck and reducing the amount of time you spend optimizing. So again, going from large problem, however big you want to run, down to a lower level. So once you figure out if MPI or communication is a problem and you knock those off, then you definitely want to look at loop optimization. Then you want to look at things like, should I parallelize this loop? Should I vectorize this loop? That sort of thing. So just keep in mind that you're going to get the best from your efforts if you analyze your code at the intended scale that you're going to run it at initially. And then you can play with different job sizes later. So here's a set of experiments that we suggest. So if you want to start, if you're starting off first and you just want to know where your slowest areas are with your most notable bottlenecks, you run at the representative job size and you just use the Perftools-lite mode. This is the lowest overhead mode. It's good for examining basic characteristics of a program. And you can actually run it if you want to do scaling analysis. You can use Perftools-lite and run on a small set of nodes, then go larger and larger and kind of see how the applications change, or the routines within your application change in how long they execute. Okay. So after you understand where your slowest areas are in your code, you want to make sure that communication isn't a problem. So I'm going to jump down to the third bullet here. So using Perftools-lite will tell you right off the bat, is MPI dominant? It will also tell you if there's a load imbalance between ranks. And so that, again, is your go-to first experiment. Then if you do have MPI communication issues, then you can use the Perftools experiment, that instrumentation module, and just collect MPI statistics. This will control the amount of data you're collecting, as the question earlier came up. If you just look at MPI routines, because you're going to focus on communication, you can collect more detailed, specific information. So the types of things that we can provide you is message sizes, how long the routines took to execute. We bin the message sizes so that you can see, are most of your messages small, or some of them medium, or most of them large. We also can show you who communicates with whom. You can get a mosaic and apprentice too, so you can get a lot of information about your communication with that experiment. So let's say now you know where your slowest areas are, you've kind of tackled those, you've tackled your communication, that's not dominant anymore, and now you want to focus on loop optimization. So an interesting thing to do there is your light loops experiment and your light HBM experiment. Now for KNL, it's very useful. Both of these are very useful because a lot of times you may want to add OpenMP to smooth out the edges within the node. You may also want to look at your memory bandwidth sensitivity if you want to look at using cache mode versus flat mode. So these two experiments, the light loops, what that's going to do is that's going to sort your loops in your application from the loops that have the most amount of work to the loops that have the least. This is something that uses the Cray compiler. So earlier I mentioned there's a few things that require the Cray compiler, and this light loops experiment does. This will give you, instead of your profile by functions, this will give you basically your top time-consuming loops. This is very useful because now you know which loops to go after if you're wanting to tune or add OpenMP. You can tune loops by you don't have to add OpenMP. You may want to look at vectorization. And that, as I mentioned earlier, generating a compiler listing is useful because now you know which loops are the dominant loops in your application. You can look at what the compiler already did to the loops or did not do to those loops. And then it gives you some idea, should I be cache blocking? What should I be doing with these loops? The light HBM experiment, this one is very helpful if you want to understand if you have memory bandwidth issues. As I mentioned, with using MCD RAM on KNL, but also just plain tuning loops. So this can be used on other processors like Haswell as well. We can produce memory traffic hotspots or show you where your memory traffic hotspots are. Again, this is the Cray compiler experiment. So those two loop optimization experiments need the Cray compiler to be able to use them. So to recap, Perftools-lite can be used with any compiler. You build your program with that module loaded. You run, you get those statistics out at the end. You can play around with the data. You can run pat report. And then as you want to tackle analyzing a code, you start with your large typical job size that you're going to eventually run with. And then you see if you have communication issues, you can focus on that. And then you can go to the fine-grained loop and memory bandwidth analysis. Okay. So just for later, in case you want to look at loop analysis or high bandwidth memory, this is how you would do actually I think I have an example of the loop optimization, and there's one other, but it's not HBM. Again, you use this just like you loaded Perftools-lite. In this case, you load Perftools-lite loops, you build your program, and you run. So the difference here is it needs the Cray compiler. So I've done a module load Cray programming, made sure the Cray programming environment is loaded, and then I loaded the Perftools-lite loops. Then I built my program. I typically add minus h list equals a because I'm going to get some additional information, which is very useful. You don't have to do that. The one thing you do have to do with this experiment is you have to add minus hpl. This is a program library. The user specifies the name of the directory to create, that the compiler will create, and that is needed if you ever want to use reveal. So if you want to view your loops through reveal or your compiler listing through reveal, you need to have this program library. And this is something that you would have to change in your makefile in order to produce. Because we don't pollute the namespace, the user needs to provide that directory name. And then the compiler will create it and put a bunch of information in there about the program that the performance tools can then use. And then you run your program, just like you did with the light mode. And now instead of getting a profile by functions, you're going to get loop information. Same style, sent to standard out just like before. So for MPI, that was the other experiment I had an example of now that you could use as a cheat sheet here too. So you load Perftools instead. And then this gives you an example of not using the simple mode. This is, I'm going to instrument my program, I'm going to run it, and I'm going to generate a report. And so there's more steps than in the simple interface, in the light interface. So here I have to instrument with pat build utility minus GMPI on your program that you built. And what happens is we actually create a new program. We create a version of the program with the same name plus pat at the end. So then you have to change your job script to run the instrumented application instead. So then there's a little bit more maintenance or a little bit more tweaking of things to do with this mode. And then when you're done, when the program is finished executing, you're going to process the data with the pat report utility. And this will produce a full report like we were doing from light mode when you ran pat report. But the user has to do it themselves. And this will happen on the login node as opposed to on the compute node. So the pat build happens on the login. Then you run on your compute nodes with your plus pat binary. And then back on the login, you create your report with pat report. So there's a few more steps, but hopefully this isn't too much and can be followed. This recipe can be followed. Again, the light mode is the easiest to use. And so hopefully if you're not tuning a lot, that's the thing you go to first. And it does give you a lot of information. So just in conclusion, basically we try to offer capability that helps reduce the amount of time that you're going to spend tuning your code. And we provide a simple interface plus a lot of extra capability for when you have more complex application that you want to analyze. So hopefully we've got the best of both worlds where it's something easy to get a basic profile of your application, but then we have the tool and the capability available when you have very large, tricky applications. So with that, I think I'm done. Are there any questions?
Looks like we might have one question in the chat.
Okay.
So Paul Kaufman was asking if we have questions about interpreting the pat report results, where can we get those answered?
So it depends on the questions that you have. The first thing that I would do is you can try the pat help utility. There's a category called pat report, and that will give you information about how things are typically aggregated, what things mean. You can also look at the user guide to try and get some insight there. Other than that, the best thing to do would be to, if there are typical questions that we get, if we get repeated questions, we try and put observations or information in notes in the output that hopefully answers those questions. If not, open a ticket. If something doesn't make sense, we can try and clarify it. One example is when we show the memory head watermark, people were asking, well, where is that information coming from? And they ask that often. And another question is, what do certain file names mean that show up in the I/O statistics? And so what we ended up doing, because those were common questions, is we put in the notes section a little bit of a, we say, well, this is where we got the data for the memory head watermark, or this is what this file name typically means with your I/O statistics if it's not one of your files from your application. So we try, when people ask questions, we try to put that information back into the tools. So if you have some questions that come up often, we'll be more than happy to try and address those.
Okay, and we had another question from Mike. The question was, is there value in working through optimizations from different compilers?
Is there value working through optimizations or with, I'm sorry, say that again?
Well, the question was, is there value in working through optimizations from different compilers? That might need a little clarification, Mike.
Yeah.
Are you asking, is it worth trying different compilers and different optimization levels, or trying to generate, performance data using these, or would they have any impact on the result, the capabilities of the tool? So I guess one question would okay, so Mike says yes, do the same study with different compilers.
Okay. So if you wanted to see how one compiler handled the code and handled the loops in a code versus another compiler, you could certainly profile. You could take the exact same code, build it with the different compilers, and run the Cray Perftools-lite experiment and see what the differences are. One thing I would highly recommend if you do that, it's easy to see where a function changes. Make sure that you have enough, you run the program long enough so you get a representative sample that's not just noise. You also want to look at any kind of listing information or optimization messages that come from that particular compiler as you're comparing them. So you'd want to see, okay, if a particular function showed up as a hotspot in your application, what did the compiler do to those loops in that application? And so you probably need a combination then of looking at the performance tools, which will highlight the line numbers where there are hotspots, but then also what did the compiler do? So yeah, that can be done. It can be useful to see, and even within a single compiler, if you want to try different optimization levels and see what happened, look at the listing to see what the compiler did to the code, but also then see what the performance impact is with Perftools-lite.
Okay, and we had a question from Ray Loy, and the question was, from your work profiling on KNL, is there any performance pitfalls that come up most often?
Performance pitfalls. Okay, so I guess the most interesting thing that we've seen is that the pure MPI solutions tend to perform very well, applications that have pure MPI. So people who have added OpenMP to their programs, they have not always seen, so let's say they add OpenMP within a node and then they have an MPI rank per NUMA domain or an MPI rank per node that communicates off node. Those models tended to not perform as well as the pure MPI that we found. And I think a lot of it has to do with the levels of cache, the processor speed, and just what happens with MPI and how the caches are utilized, or if your data still is able to stay resident in cache as long or not. So we have seen some behavior there. Typical, other than that, it's really dependent on the application. So some applications run really well in cache mode, for example, with MCD-RAM. Some of them run better in flat mode. A lot of them fit completely in the 16 gig of MCD-RAM when configured in flat, and so that performs very well. One thing that we found, I guess, with our high bandwidth memory analysis is sometimes it was better to have a split mode with some flat and some cache, like 25% still allocated as cache of the MCD-RAM. And the reason we saw that is because we were getting a lot more TLB misses or a lot more TLB page walks if you did completely flat mode. And so that was something, as if you have a code that's memory bandwidth sensitive and you want to switch to using flat, you're going to take the penalty because there isn't an L3 cache and there can be more TLB walks. And so having a combination may be something interesting to try. Those are the only things I can think of right now. It is, I guess I should say, KNL is a pretty interesting processor because of its speed. It's a little bit slower processor than the other traditional Xeon processors. So what it did for us, which was very beneficial, is it taught us, even in the performance tools, we had to be careful about how the code was executed. We had to go in and make sure we weren't branching very often, so how did we impact execution? The MPI library had to go through and be very careful about how it executed on these processors, and so did the compiler. And so it's very sensitive. The processor is very good at calling out inefficient code. So those
Okay, and
good
we had
learning
one last
experience.
question.
Yeah.
One last question that sort of relates to what you just said. It's from Dario, and the question was, tools like Valgrind use virtual machines in order not to affect performance of the applications we are profiling. How does PerfTools deal with this situation? And I'm sort of taking the question as, how do you minimize the interference with the, what you're actually trying to measure? And
Oh, yeah, sure. So as I mentioned earlier, Perftools-lite is our least intrusive. It has the least perturbation on your application. As you're doing things like tracing, and we're actually doing a timestamp at the beginning and the exit of every function, that can be much more harmful, or it can perturb the application more. One of the things that we do is when we are doing something like tracing, we subtract the overhead. So the overhead that we produce or that we incur because of our performance tools, we actually go ahead and subtract that out. And so what we try to give you is, even though the application took longer to execute or could have taken longer to execute than it would have without the performance tools collecting data, the relative behavior should be the same as if you didn't have, or as close to the same as if you didn't have performance tools. And in a full report, at the very bottom, we have some additional details section. And in there, you'll see the overhead that we subtracted. So if you were questioning, for example, you did some runtime summary tracing, you're questioning how much overhead we created, and is it actually changing the behavior of the application, you can look at that overhead that we measured. So we do measure the overhead that we incur, and we try and subtract it out. So we're trying not to perturb the application behavior, even if we execute longer than the application originally did.